Hello everyone, my name is Jorge Delgado and I'm from Indiana Nanociencia in Madrid, and I'm going to present you this work that was published recently, in which we present a theoretical XUV-pump XUV-probe experiment in glycine in order to study a charge migration phenomenon, which has been associated to specific fragmentation channels in amino acids. It is important to remark that the part corresponding to the pump pulse and the cationic propagation has been fully completed, whereas the part corresponding to the probe pulse and the decation propagation has yet to be completed and has only been described qualitatively. Now, if we move to the results, and in particular to the results of the nuclear dynamics of the cation, what we observe here in these pictures is that is the time evolution of the CN bond and the CC bond for all the cationic trajectories, without accounting for the action of the pulse. Considering that the color bar indicates the initial cationic stage in which the trajectory starts the propagation, we can conclude that CN elongation and fragmentation can be associated to initial high cationic states, and CC elongation and fragmentation is associated to initially low cationic states. If we consider now the action of pulses with different central frequencies, and considering that darker lines indicates higher probability, what we can observe is that 12eV ionization favors fragmentation through the CC bond, and as we increase the central frequency of the pulse, we are favoring fragmentation through the CN bond, being this one slightly higher for the case of the 12eV pulse than for the case of the 20eV pulse. So why is that? That's because we use pulses with different central frequencies that creates a different cationic wave packet, which are the results of different coherent superposition of cationic states. So in the case of the 12eV pulse, what we are doing is populating mainly the two lowest cationic states. That's what explains why CC fragmentation is more probable in this case. And as we increase the central frequency of our pulse, what we are doing is to populate higher cationic states, which are responsible for CN elongation. So from this picture and the previous picture, we can conclude that we can favor different fragmentation dynamics by varying the central frequency of the pulse. Finally, we move to the case of the decation. What we have done is to perform a qualitative study of three selected cationic trajectories. One that shows CN fragmentation, another one that shows CC fragmentation, and finally one which doesn't show fragmentation at all. If we consider in particular the picture concerning to the CC fragmentation, we observe at the top the pump-probe scheme and the nuclear configurations, and below the distribution of the charge for the different fragments after 45 femtoseconds of the cation propagation, being the x-axis the delay between the pump-probe. After a certain time delay, it suggests that the charge is very well distributed between the two fragments and that CC fragmentation is indeed observed after the cation propagation. These results and the other results suggest that it might be possible to retrieve a signature of the dynamics initiated by the pump pulse, but we still need to complete the full decationic pictures to reach to further conclusions. So that was all. I just want to thank you for your attention, and thanks to my supervisors and collaborators of these projects, and of course I cannot forget for the funding and the computational resources. Thank you very much.